Good evening, everyone. Welcome to the June presentation of An Evening at Skidaway. Our speaker this evening, Dr. Cliff Buck, is a very interesting talk on one of the hottest, no pun intended, non-COVID science issues out there today, climate change. Dr. Buck is a chemical oceanographer. He received his bachelor's degree from Lehigh University and his doctorate from Florida State University. He joined the Skidaway University of Georgia faculty in 2013. Dr. Buck, take it away.
All right, thank you, Mike. Welcome to you all. Welcome to our Evening at Skidaway presentation this evening. I appreciate you making the effort to join us virtually. My name is Dr. Cliff Buck, and I'm a chemical oceanographer here at the UGA Skidaway Institute of Oceanography. Tonight, I want to present some information regarding climate change and the role people have in the warming that has been observed over the last several decades. But please note, I am not a climate scientist. While my research focus has some implications for the global carbon cycle, I do not directly study climate, and nothing I show tonight is my own original research. The issue of climate change has become somewhat contentious, though it was not always so. Over the last decade or so, not coincidentally, occurring along with the expansion of social media sites like Twitter, groups seeking to cast doubt on the role people have in causing climate change have found a platform to sow confusion and doubt about the science. As a result, so-called myths have gained traction. Much like in the classic movie The Princess Bride, when Inigo Montoya is trying to update the dread pirate Roberts as to the disposition of Princess Buttercup, I must sum up because there's just too much for a single presentation. So, in the interest of time, we will focus on a few key topics. First, we will cover some of the physical basics of the Earth's climate. Then, I will show you some examples of the evidence scientists have gathered which support the premise that our climate is warming. We will then look at 3 specific climate myths and why they do not stand up to scrutiny. Now, for our purposes, a climate myth is an idea presented in a way meant to cast doubt on our understanding of climate change. These myths are a type of misinformation that is spread by mistake or, in some cases, with the intent to mislead the general public. Often, this misinformation is repeated across many forums to increase a person's familiarity, thus creating the illusion of truth. Climate myths can create the impression that there is reasonable debate within the scientific community about some aspect of climate change, when there is, in fact, no debate. The strategy is similar to that used by tobacco companies in the 60s to perpetuate the erroneous belief that smoking was harmless. Climate can be thought of as average weather. The Earth's climate tends to be relatively stable over long periods of time, though it does change naturally. One of the best understood mechanisms of natural climate change is caused by variations in the Earth's orbit. These variations are commonly referred to as Milankovitch cycles and have a regular periodicity and correspond to changes in climate that are recorded in ice cores and sediment records. Scientists often use 30-year periods to define climate norms. The image shown on the right of this slide is meant to visualize the difference between weather and climate. The image is from a video by Neil deGrasse Tyson and shows him walking a dog along a beach. As he walks steadily along the shore, which is shown in red, the dog runs back and forth investigating every smell, critter, and grain of sand that catches its eye, as dogs do. This path is colored blue. You can think of the dog as the weather and Tyson's path as climate. Another way to think of it is that weather is your mood, while climate is your personality. Now, it seems obvious now, but it was not until the 1820s that scientists realized that all energy that maintains the Earth's temperature came from an external source, the sun. But energy must be lost as well, or the Earth would overheat. Now, Joseph Fourier is credited with determining that the only way that a planet can lose energy is by emitting radiation. And this is because space is a vacuum, so energy or heat is not lost by conduction. If you are a science fiction fan, this begs a fun thought experiment. So one could calculate how quickly a person might lose heat if they found themselves spaced or cast out of an airlock, like in the Expanse series or books. Now, in 1856, an American woman named Eunice Foote conducted experiments that showed containers of carbon dioxide would reach higher temperatures when exposed to sunlight than would containers only holding air. Or as she reported, the receiver containing this gas became itself much heated, very sensibly more so than the other. And on being removed from the sun, it was many times as long in cooling. And because of her gender, her contribution has been largely overlooked. And she was not even given the opportunity to present her findings to fellow scientists. John Tyndall's work a few years later confirmed this greenhouse effect. He found when the heat is absorbed by the planet, it is so changed in quality that the rays emanating from the planet cannot get with the same freedom back into space. Thus, the atmosphere admits of the entrance of solar heat, but checks its exit, and the result is a tendency to accumulate heat at the surface of the planet. Now, obviously, we have learned much more about the physics underlying the planet's climate, but the point here is that scientists have recognized the fundamental aspects of the Earth's energy budget since before the American Civil War. The work of Fourier, Foote, and Tindall was just the start. As the 19th century came to a close, their ideas were advanced by Swedish scientist Solarirradiance, who calculated how much the planet would warm if the concentration of carbon dioxide in the atmosphere were to double. In the 1940s, Guy Callendar observed that global land temperatures were rising and suggested that carbon dioxide was the cause. In the late 1950s, Charles Keeling began direct measurements of atmospheric carbon dioxide, which continue today. This data provides a record of human impacts on atmospheric composition. Around this same time, the first climate models were created by harnessing the power of computing. And today, we are able to use satellite and ground sensors to directly measure the impact of carbon dioxide on the planet's energy budget. And sophisticated climate models are making great strides in helping scientists understand the complexities of the climate system. Now, some of the basics. So on the previous slide, I mentioned the planet's energy budget, and I think it is worthwhile to spend a little time on the topic. In its simplest form, we can think of the planet's energy budget using a simple box model. In the example here, I represents the energy entering the system, and O represents the energy out of the system. The system, or the Earth for our purposes, is the blue box. Now, delta X over delta T simply refers to the change in the amount of energy within the system over time. If the energy in is equal to the energy out, then the budget is in equilibrium, and the planet would neither warm nor cool. Logically, it follows that if the input energy exceeds the output, then the planet will warm. That warming will continue until the output equals the input, because fundamentally, this is a process which tries to reach equilibrium. And at this point, we need to talk a bit more about electromagnetic radiation. Electromagnetic radiation covers a wide range of wavelengths, and all sorts of things that you may not think about as radiation, like radio waves, and others you might, like X-rays, fall somewhere along that range. When we think of sunlight, we are speaking about the visible spectrum, as shown in the figure here. Note that the visible spectrum is actually a quite narrow band within the broader context of electromagnetic radiation. This band, spanning from about 400 to 700 nanometers, is emitted by the sun and hits the Earth's atmosphere. Now, to put that in perspective, 1 nanometer is equal to 1/1,000,000th of a millimeter. Some of that radiation may be reflected by clouds or scattered by particles in the air, but this solar radiation largely reaches the Earth's surface. Also note that the shorter the wavelength of the radiation, the higher the energy. And this is why very short wavelengths associated with ultraviolet light and gamma rays can be so damaging to biological material. Now, the Earth itself also emits radiation because all objects that are warmer than absolute zero emit radiation. The flux of energy from an object is governed by the Stefan Boltzmann Law, which is a mathematical expression relating an object's energy flux to its temperature. This phenomenon is plotted in the figure on the right. Note that there are several curves, each associated with a given temperature. Now, the higher the temperature, the more intense the radiation, and the more the radiation is centered on shorter wavelengths. The high energy output from the sun is similar to the curve corresponding to a temperature of 6,000 Kelvin. Most of the radiation emitted at this temperature is shown at shorter wavelengths that include the spectrum of visible light. At longer wavelengths, centered at about 10 microns, we see the energy output of the Earth. This energy output is a function of the temperature of the Earth's surface, which is represented here as 303 degrees Kelvin. Note that this characteristic wavelength falls within the range of infrared radiation. You're already familiar with this concept, even if you did not think about it in this context. If you look at the statues in this picture, we know that the brighter statue on the right is hotter than the statues to the left. This is because at the higher temperature, the statue is radiating within the visible spectrum. If it were to cool, then the radiation would move out of the visible and into the infrared, and your eye would no longer be able to see the radiation unless you used an infrared sensor. So here it's another diagram showing that difference between the radiation that comes from the high temperature sun at 6,000 degrees Kelvin and comparing it to that 303 degree Kelvin emitting temperature of the Earth. And again, you can see that the 303 degree Kelvin of the Earth is centered around 10 microns, which falls within the infrared. And we can see that infrared radiation being emitted by the planet as shown by this image of Earth from space. Now let's look at how this balance of energy in and energy out work on our planet. First, we're going to look at an example of an energy balance model that assumes that there's no atmosphere at all. And we know that the incoming solar radiation hitting the Earth is equal to 342 watts per square meter, as shown by the large yellow arrow pointing towards the surface. We also know that about 30% of this radiation is reflected back because of the planet's albedo. The planet's albedo is 0.3. The term albedo refers to the reflectivity of a surface, so this means that about 30% of that incoming solar radiation is reflected by the upper atmosphere. Now, for comparison, the albedo of the ocean is about 0.06, and sea ice is approximately between 0.5 and 0.7. So 30% of 342 is 102. So the atmosphere will reflect 102 watts per square meter, as shown by the smaller yellow arrow pointing away from the surface. This leaves 240 watts per square meter to be absorbed by the Earth's surface. In this case, because there is no atmosphere in our model, the amount of energy absorbed by the surface will be equal to the amount of energy that the surface emits. From Stefan Boltzmann, we can calculate what the equilibrium temperature would be in this scenario. And we arrive at a surface temperature of 255 Kelvin, which is equivalent to minus 18 degrees Celsius. Now, we know this is not the case because the Earth is not a ball of ice. The reality of Earth's energy budget is obviously much more complex, and you will immediately see we have more figures to deal with. The Earth still receives the same amount of energy from the sun, and 30% is still reflected by the albedo. But the real atmosphere is unlike the first model and does absorb some incoming radiation. In addition, the Earth's atmosphere is heated by processes that are unrelated to radiative fluxes. For example, warming of the surface by solar and terrestrial radiation causes air to warm and rise by convection. This transfers heat from the surface to high in the atmosphere and also carries moisture as well. Now, there's a few things to note in this diagram. Observe that the amount of solar radiation reaching the planet's surface is equal to 161 watts per square meter. When we compare that to the amount of absorbed terrestrial radiation being returned to the surface, we see that this latter term, the amount emitted by the atmosphere, is more than twice as large as the amount coming from the sun. Now hold on, sidebar. Ultimately, the sun is the source for all of that energy, so there's no energy being created by the atmosphere. We have seen that the surface temperature would be much lower without an atmosphere to act like insulation. Thankfully, in the real world, the atmosphere is there to slow the rate of cooling and keep the planet at a temperature that has allowed the proliferation of life and no less importantly, allowed for human civilization to develop. Because of the atmosphere's impact on downwelling radiation, the average surface temperature on the planet is 15 degrees Celsius, allowing for things like liquid water and conditions suitable for life. Now, thus far, I have focused on describing the Earth's climate system in various states of equilibrium And this makes sense because the physics underlying radiative transfer is fundamentally about objects moving toward equilibrium. In our case, we are talking about an equilibrium between the energy absorbed by the Earth and the energy lost back to space. The Earth's temperature will rise until the amount of radiation entering the system equals the amount exiting. It's now appropriate to consider factors that disrupt the equilibration process or create a difference between the incoming and outgoing radiation. These factors are called forcings or feedbacks, depending on how the mechanism impacts the climate. A radiative forcing causes some change in the radiative flux at the top of the atmosphere. These can be either a positive or negative direction, with a positive forcing being one that creates a warming effect. The chart on the right has some examples, including both natural and anthropogenic or human-created forcings. The x-axis plots the strength of these forcings in watts per square meter, which is a standard unit for energy flux. Note that the total anthropogenic forcing is nearly entirely due to greenhouse gases, including carbon dioxide. In fact, the 2013 International Panel on Climate Change, or IPCC, report finds that it's very likely that all of the observed warming since 1950 is due to the increase in greenhouse gases in the atmosphere. This increase in radiative forcing is shown in this table. If we normalize to conditions in the year 1750, which is chosen to represent the pre-industrial period, then over time we see that radiative forcing has increased by 2.29 watts per square meter as of 2011. We also see that the rise in forcing has accelerated. Now, the next IPCC report is due in 2022, and we can expect these figures to be updated to reflect the changes observed over the last 10 years or so. At this point, I think it is important to get a sense of how humans have changed the Earth's carbon cycle. To do this, we will return to the idea of a box model. In this case, several boxes that are linked together. In this video, each box represents a reservoir of carbon. There's a box for the atmosphere, 2 boxes for the ocean, a box for the terrestrial biosphere, and one box for fossil fuel deposits, which is shown in red. As the animation proceeds, you will see carbon represented by dots moving among these reservoirs. Now, each of these dots represents 1 gigaton of carbon, which is 10 to the 12 kilograms or 2.2 trillion pounds. Now, for context, each year, all the countries in the world collectively emit about 10 gigatons of carbon, or 10 of those red dots. You should note that in the pre-industrial period, all these reservoirs are roughly in balance, and we don't see an accumulation in the atmosphere. The concentration at the start of the video was 276 ppm of CO2 in the atmosphere, which equates to about 588 gigatons of carbon. But as time goes forward, keep an eye on the amount of carbon in the atmosphere. At first, the concentration was slowly creeping upward, but ultimately starts to increase much more rapidly. This increase is due to the burning of fossil fuels. The dots representing carbon are moving between the reservoirs very quickly, but you may start to see the red dots being redistributed from the fossil fuel deposit reservoir into the atmosphere, as well as into the ocean and the biosphere. If we focus on the final frame of the animation, then we can see how carbon from fossil fuels is redistributed through the Earth's carbon cycle. Each gigaton of fossil fuel carbon is colored red, and we can see how those red dots are distributed through the other reservoirs. This is important because all of this carbon, thankfully, does not stay in the atmosphere. If it did, we would be in far worse shape than we presently find ourselves. For example, it is estimated that the ocean has absorbed about 30% of the carbon that we have emitted. This absorption, however, does not come without a cost. This extra carbon is causing a decline in the pH of seawater through a process termed ocean acidification. Nonetheless, the concentration of carbon in the atmosphere has increased by about 50%. We can compare the pre-industrial concentrations in the atmosphere, which were, I'll remind you, were 276 ppm, or parts per million, and 588 gigatons of carbon. We can compare those numbers to what they were in 2017. At the conclusion of the simulation, the concentration has risen to 406 parts per million and 865 gigatons of carbon, an increase of 130 parts per million and 276 gigatons. Again, this carbon has come from the fossil fuel deposits, which show a loss term of 424 gigatons. Now, of course, 424 is larger than 276, and that difference is accounted for by all of that fossil fuel carbon that ended up in the ocean and in the living biosphere. And we are now at 419 parts per million, which is the highest atmospheric CO2 concentration in over 4 million years. And unfortunately, much of these carbon emissions have been in recent years. The chart on the right here shows the percentage of fossil fuel emissions that have occurred in a given person's lifetime. Using myself as an example, more than 60% of all fossil fuel emissions have occurred in my lifetime. The concentration of carbon dioxide in the atmosphere when I was born was 335 parts per million. I find this remarkable, especially because we have long known that unchecked carbon dioxide emissions will cause climate change. To borrow a term that we have all become familiar with, this is a curve we truly need to bend down. We know that greenhouse gases like carbon dioxide are increasing in the atmosphere, but what makes a greenhouse gas? We need to understand what makes the so-called greenhouse gases such potent warming agents. This figure shows two depictions of a carbon dioxide molecule. And these diagrams are meant to show how absorption of infrared radiation causes the molecule to vibrate. It is that vibration that makes these molecules greenhouse gases. The molecule can then transfer this energy by bumping into other molecules in the atmosphere or by re-emitting the energy as radiation. Both processes slow the emission of radiation from the Earth and thus cause the Earth to cool more slowly than it would in the absence of carbon dioxide. We perceive this slowdown of the rate of cooling as warmer temperatures at the surface. Now, this figure shows how radiation is transmitted down through the atmosphere. The top pane shows how much radiation passes down from the sun through the atmosphere in red, and the bottom pane shows how much is absorbed or scattered in gray. You can think of these two plots as opposites. When the gray areas are largest, the more radiation is being absorbed. In parts of the spectrum where absorption and scattering are highest, with lots of gray shown, then you won't see the red signal. About 70% is transmitted because, if you recall, the Earth's reflectivity sends about 30% back to space. At the very far left, we see that most of the UV is blocked. And that is a good thing because of how harmful that radiation is to organic material. Next, let's look at the radiation coming up from the Earth's surface to space. The two carbon dioxide vibration patterns shown on the left correspond with interactions at 4 and 15 micrometers. We see that effect in absorption spectra that I've circled on the bottom right. The large gray peaks indicate that carbon dioxide is an excellent absorber of a radiation at those wavelengths. As the concentration of carbon dioxide in the atmosphere rises, more radiation at those wavelengths is absorbed. You might think of parts of the spectrum that allow the large blue curves, which signify infrared radiation passing through them to space, as windows. Adding greenhouse gases makes those windows smaller. Let's look at this another way. Imagine a photon of infrared being emitted from the Earth's surface. If that photon were emitted in the year 1900, it would need to pass through 11.4 million molecules of CO2 before it could reach space. But if that photon were emitted today, the number of potentially interfering molecules of carbon dioxide would be 17 million. This rise increases the likelihood that the photon will be absorbed by carbon dioxide and raises surface temperatures by making it that much harder and slower for infrared energy to reach space. You're probably noticing that water vapor seems to be responsible for a great deal of absorption as well, and this is completely true. However, the concentration of water vapor in the atmosphere is what is termed a climate feedback, which is a process that amplifies or dampens the temperature response to a climate forcing. Put very simply, the warmer the atmosphere is, the more water vapor it can hold. And because of the ability of water vapor to absorb infrared radiation, this further adds to that warming. But of course, water vapor also condenses into liquid water. If there were no carbon dioxide or other greenhouse gases, most of the water vapor in the atmosphere would condense out, and its impact on the Earth's energy balance would be much less. We see many lines of evidence that show our climate is changing. There is an accelerating rate of sea level rise. The extent and age of Arctic sea ice is in rapid decline. The ice sheets in Greenland and Antarctica are losing mass. We can observe changes in growing seasons and in animal migrations. We also see a rise in global temperatures. This figure is from NASA Goddard and shows the temperature anomaly relative to a baseline period of 1951 to 1980. Since that time, the planet, including land and ocean surface observations, has warmed by 1 degree Celsius. This figure is from a study of global temperature over the last 2,000 years. We can see that the planet's temperature was relatively stable over much of that time. The chart also indicates periods when it has been thought that global climate deviated from that stable temperature. The medieval warm period, highlighted in red, was once thought to be a global phenomenon when the planet was warmer than today's temperature. But recent work that includes more temperature records from the ocean, southern hemisphere, and other remote regions has shown that, in fact, the so-called medieval warm period was a time of only regional warming, which was focused in the area around the North Atlantic. Given the Eurocentric bias in historical record keeping, it is not surprising that this period had long received a disproportionate amount of weight and attention. The other notable period before present is the so-called Little Ice Age, which is highlighted in blue. This period of relatively cooler temperatures was likely caused by an unusual amount of global volcanic activity, which created a negative climate forcing. The rapid warming of the modern period is clearly evident in the record and far exceeds any warming over the last 2,000 years. Now, this chart was published just this year. It takes the temperature records back 12,000 years. We know that global temperatures, which were compiled from a number of records, rose about 12,000 years ago as the planet entered what is called the Holocene period. This warming marked the end of the last glacial period when the ice sheets retreated. Temperatures then remained relatively stable before starting a slow decline in the last few thousand years. Not coincidentally, during this time, humans were busy creating civilization. And now, global temperature is much higher. These temperature records show more evidence for what is commonly called the hockey stick, which was first identified by Dr. Michael Mann in the late 1990s. This is a reference to the sharp uptick in global temperature, which somewhat resembles the blade of a hockey stick, relative to the long handle of stable temperature through most of the Holocene. I hope that you now have a good mental picture of how climate works and why the concentration of the greenhouse gases are so important. It's clear that people are changing the composition of the planet's atmosphere, and that change is causing the planet to warm. Unfortunately, the science is often misrepresented in the public space. With the proliferation of social media, groups that are motivated to undermine action on climate change have found a platform to spread confusion and doubt on the subject. It can be useful to think of this misinformation as climate myths. My goal with the remaining time is to give a few examples and explain why these myths do not stand up to investigation. At this point, I need to credit one of the better websites that is dedicated to providing scientifically sound information. The website called Skeptical Science is dedicated to providing these sorts of resources, and I often use it in my teaching at UGA. In fact, I contributed an endorsement that is featured on their page. This endorsement is likely the only time my name will appear on the same webpage as the likes of Michael Mann and Catherine Hayhoe, but I will take it. Skeptical Science has examined nearly 200 arguments that are meant to cast doubt on the science, and I encourage you to check them out. One common argument you might come across is that changes in the intensity of the sun are causing our climate to change. And of course, at first, this might seem to make a ton of sense, because the sun is the source of all the energy that drives Earth's climate. The climate myth blaming the sun focuses on a short cycle in solar activity, which has a regular 11-year period. This cycle is recorded in the prevalence, or not, of sunspots on the solar surface. The idea is that during periods with lots of sunspots, the sun is putting off more energy as compared to times of little to no sunspots, as shown in the image here. The figure on the lower left shows about 400 years of sunspot records. Now, the terms Maunder minimum and Dalton minimum refer to periods in the past when there were unusually few sunspots. The Maunder minimum roughly coincides with the period of cooler temperatures called the Little Ice Age, and this coincidence is often used as justification for the climate myth that solar activity is driving modern climate change. Put simply, the argument amounts to, it was colder during the Maunder minimum when there was very few sunspots, so it must be warmer now due to sunspots being more prevalent. But that reasoning simply does not hold up to scrutiny. NASA tracks changes in solar irradiance, or the energy coming from the sun. And this plot here provides a record of both the solar irradiance in yellow and global temperature anomaly in red. The darker lines represent the 11-year average of both of those data sets, and that removes the variability from that 11-year solar cycle. But what we observe from the data is that while the two data may have tracked well up until about the mid-20th century, there's a clear departure after that. This is precisely when we believe that human greenhouse gas emissions really took off and became the dominant climate driver. Since then, solar intensity has gone down while temperatures have climbed. Here we see that comparative plot of climate forcings that I introduced earlier. Notice how insignificant the radiative forcing from solar irradiance is. In addition, if the sun were responsible for global warming, we would expect to see warming throughout all layers of the atmosphere, from the surface all the way up to the stratosphere. But what we actually see is warming at the surface and cooling in the stratosphere. This is consistent with the warming being caused by a buildup of heat-trapping gases near the surface of the Earth, and not by the sun getting hotter. There's even a flip side to this particular piece of misinformation. Some argue that a solar minimum is coming and that it will lead to global cooling. Some websites go as far as to highlight cold weather around the world in an effort to prove that the planet is cooling. However, the peer-reviewed literature tells a very different story. A study from 2011 found that since 1979, solar activity had a very slight cooling effect, which is not sufficient to counteract the warming from anthropogenic emissions. The figure here shows a comparison of modeled temperatures into the future. These projections indicate that a grand solar minimum, or a period of long duration period of low solar intensity, would only suppress global temperatures by a few tenths of a degree. So no, you do not need to hoard food in anticipation of the next glacial period. Another common climate myth is that CO2 can't possibly be responsible for climate change because it is a tiny fraction of the atmosphere. Setting aside for the moment the subjective nature of comparing relative amounts to define something as small or tiny, let's investigate if the amount of CO2 is truly too small to matter. Now on the right, we have the relative abundance of gases that make up most of the atmosphere. What is obvious is that most of the atmosphere is nitrogen and oxygen. It's a good thing too. We also see that carbon dioxide is 0.04% of the atmosphere. Now the amount is actually about 420 parts per million as of June 3rd. And I think this bears repeating. This is the highest atmospheric CO2 has been in over 4 million years. But either way that you look at it, whether these numbers are percent or parts per million, they only tell you the amount of gas relative to everything else in the atmosphere. And this is not the best way to think about the impact of the gas. You know this intuitively if you have ever traveled to higher elevations. For example, when I visited Breckenridge, Colorado, which is at an elevation of about 9,000 feet, I found, among other issues, that the thin atmosphere made normal activities like walking upstairs difficult. But the proportion of the atmosphere that is oxygen is the same in Colorado as it is in Georgia. So why should I struggle? Because the atmosphere itself is thinner at elevation, meaning there are fewer oxygen molecules at 9,000 feet than there are at sea level. What truly matters is the number of carbon dioxide molecules, not the relative proportion to non-greenhouse gases like nitrogen or oxygen. We can clearly see the impact of our activities on the amount of CO2 in the atmosphere. On the right is a record of atmospheric CO2 concentrations dating back to the pre-industrial period. The data comes from bubbles of air trapped in ice cores, which were analyzed for their respective carbon dioxide concentrations. And after the mid-1950s, when Dr. Keeling started collecting his atmospheric CO2 measurements, we have a record of direct measurements of the amount of CO2 in the air. This figure shows the amount of global CO2 emissions since 1990. The units are in gigatons of carbon, and recall that 1 gigaton is equal to 1 billion tons. This figure also includes the rate of increase for each of the 3 decades covered by the plot. The fastest increase corresponded with a period of rapid industrialization in the developing world. The slowing in the rate of growth over the 2010s was driven by a general switch from coal as an energy source, as well as the growing adoption of non-fossil fuel energy sources. Now, the decrease in 2020 was driven by the international response to the COVID-19 epidemic. But unfortunately, this downturn has reversed already, and emissions are expected to climb higher in 2021. Based on current and pre-industrial CO2 concentrations in the atmosphere, we can calculate that the amount has increased by about 50%. Once again, we revisit the IPCC's chart of radiative forcing. At the top, we see the contribution of CO2, and note that its contribution is nearly the entire amount of total anthropogenic components. So this 50% increase of CO2 in the atmosphere is the primary driver of the change in radiative forcing. On the right, I've built a plot using the website woodfortrees.org. And this data comes from the NOAA record of atmospheric CO2, and that's shown in green, and the Berkeley Earth surface temperature record, which is shown in red. The result is remarkable correlation. Now, of course, and this point is often brought up, correlation does not imply causation. However, in the case of CO2's role as a greenhouse gas, we do not rely simply on an observed correlation. We have a long record of theory and observations which underpin our understanding of causation. This statement comes from the IPCC's fifth assessment report. It is worded a bit awkwardly, but when you parse it down, they conclude that the increase in greenhouse gas concentrations due to human activity is extremely likely to be responsible for the observed rise in temperatures since 1950. Now, in the language of the IPCC, the term extremely likely means something specific. It means there is a 95 to 100% confidence in the statement. The final climate myth that I would like to discuss concerns the performance of global climate models. So climate scientists use numerical models of the Earth's climate to interrogate the system by using equations to represent the processes and interactions that drive the climate. These models are complex and can include thousands of pages of code. Running on supercomputers, climate models can both hindcast and forecast so that scientists can check model performance. Large data sets, which include petabytes of data, are input into the models. These inputs could include some of the climate forcings we have already discussed, as well as others like the concentration of aerosols in the atmosphere. The model outputs can include variables like temperature, ice extent, precipitation rates, and ocean temperature. The outputs are available on the internet as downloadable files, so researchers can compare their results with others working on similar questions. There are also ongoing intercomparison studies like the Coupled Model Intercomparison Project, which aid in assessing model performance and results. A common myth is that models simply don't work, and thus can't be used to justify any sort of climate mitigation. An example often cited is shown here. This figure suggests that the average of 102 climate model runs overestimates the warming of the Earth's climate. The models, shown in red, are compared to observations from weather balloons and from satellites, shown in blue and green. But does this figure hold up? The first issue to note is that this chart has never been submitted for peer review. If it were, some of the following issues would likely be mentioned. The chart supposedly shows bulk atmospheric temperature from the surface to 50,000 feet. However, the chart's own author testified to Congress that, and I quote, "The layer shown is known as the mid-troposphere, between 20,000 and 50,000 feet." So the observational data is not in fact relevant to the surface at all. And of course, we live on the surface and not at 20,000 feet or higher. Another key issue is that the chart lacks uncertainty ranges in both the model run outputs and the observations from the balloons and satellites. In a moment, I'll show you what that would look like, but for now, it's suffice to say that this is not the way to plot data. Other tricks used to make the divergence between model and observations appear more pronounced include misaligning the data and choosing different baselines for the model runs and observational data. Also note that the model run goes all the way to 2025, while the observational data stops in 2015. The y-axis is also truncated to give the visual impression that the models are running so hot that they go off scale. And of course, it's not valid to compare model outputs to one subset of observations and then conclude that all climate models don't work. Here we have the same model data and the same observational data, but this time plotted by Dr. Gavin Schmidt of NASA Goddard. The observations are broken out into their individual data sets rather than lumped together, and these data are set to the same baseline time period as the model runs. The model data is shown as an ensemble average, but this time the spread is shown in gray to indicate the 95% uncertainty bounds. In this case, model performance doesn't look so bad, does it? Now, the next 3 slides will show some examples of climate model outputs compared to global temperature data sets that are shown in various colors. The data sets of temperature will remain the same, with only the model results changing on each slide. This is also a good time to notice how well the various temperature data sets agree with one another. Now, this first example was put forth in 1975 by the oceanographer Wally Broecker. Now, keep in mind that climate models in the 1970s were crude by today's standards, and were also hampered because scientists had a poor understanding of how fossil fuel use would trend in the future. Nonetheless, Broecker's model was spot on in the observed temperature trend for 30 years. What is especially impressive about this work is that it was published during a time of apparent cooling of the planet's climate. However, Broecker anticipated an approaching inflection point, saying, and I quote, "A strong case can be made that the present cooling trend will, within a decade or so, give way to a pronounced warming induced by carbon dioxide." He was also among those warning against the looming problem of ocean acidification due to absorption of CO2 by seawater, but that's a different talk. Dr. James Hansen put forth a model in 1981 that included different projection scenarios to try to capture some of that uncertainty in emissions, as well as in climate sensitivity to increasing CO2. The dark line represents a growth of 4% annually in CO2 emissions. The lighter line shows a slower growth rate of 2%. In this case, the model has underestimated the global temperature, which should throw a bit of cold water on the argument that climate models always run hot. Now, if we jump ahead to 2013, the IPCC, again, published their 5th assessment report, and that included the warming projections shown here. The dark line represents the mean projection for their models that were studied. The upper and lower bounds are also included to give a sense of the spread among the model results. Note how well the models encompass the observed surface temperature data. Finally, I wanted to include a model from the early 1980s. The model shown on the right was created by scientists working for Exxon. The image is not of great quality, but what is shown is that the predicted rise in temperature as the concentration of carbon dioxide rises in the atmosphere. What is striking is that Exxon pretty much nailed it. They nailed the rate at which we would change the atmosphere. Their model predicted that carbon dioxide would reach 420 ppm around the year 2020. They were only off by a year. Their model was also close on the rise in temperature, predicting a 1.2 degree rise. And again, according to NASA, the planet has warmed by a full degree. So if someone claims that climate models don't work, just tell them that Exxon nailed it 40 years ago. So I hope you've learned a few new things about climate science over the last 45 minutes or so. As I said earlier, this isn't my area of research, so I've leaned heavily on outside resources for the figures that I have shown. I really can't recommend Skeptical Science and Carbon Brief enough. These websites feature clear writing on climate science that help sift through the complex ideas. I also need to recognize Dr. Andreas Schmittner from Oregon State, who has written a textbook on climate science and has made it available for free download. So I want to thank you for spending your time with me tonight and for your interest in the Evening at Skidaway program. I also want to encourage you to please make plans to join us for future Evening at Skidaway presentations. Our next speaker will be my colleague, Dr. Catherine Edwards, who will present on using artificial intelligence in fisheries management. The Skidaway Institute YouTube page also includes recordings of previous presentations that you may enjoy. So please be sure to subscribe to our channel and to stay informed of new content when it's posted. So thank you again, and I'm happy to take any questions at this time.
Thanks, Dr. Buck. This is Dr. Dan Anonymous, and I'm going to moderate the questions. And so if folks would like to enter any questions into the YouTube chat, you're welcome to do that. You can also email questions to me if you want at dan@uga.edu, and I can read them out. I have a couple that I've saved up over the course of the talk for you. So you've had your water. You've added your own local cooling there for a second.
A little parched.
A couple of great talks and stuff in the chat as well. So let's see. We had a question here about so as you're active on social media yourself, and one of the questions that came in was which of these, or if whether the myths that you talked about are the most sort of pervasive climate myths. So in your experience online, like which of these myths sort of does the most damage to efforts or waste the time of people who are doing this type of research, in your own opinion?
That's a really good question, and it's something that if you find yourself motivated to kind of engage in that online environment, you often have to kind of question. There are certain things that are like well worth kind of getting into and trying to explain, and there are others that are just so outlandish that you avoid altogether. I think that I selected these three to highlight for kind of for the reason that they're often cited. And again, I try not to. I think oftentimes they're shared without any kind of ill intent. It's just it's a lack of understanding, and that's my goal often, is to try to peel away the misunderstandings and like I did tonight. So I think these are three good examples. Off the top of my head, there's some other ones where one, for example, is that there's the argument that like Antarctic sea ice is increasing. So how can we be warming?
Mm-hmm.
And that particular argument ignores the fact that the processes that are involved in creating Antarctic sea ice are actually the result of melt coming from the Antarctic continent. There's this flushing of fresh water onto the super cold waters that surround Antarctica, and then they freeze up and turn into sea ice. So there has been, the trend in Antarctic sea ice is not as clear as it is in perhaps the Arctic.
Mm.
And another good example is it's really basic, but there's this idea that because climate does change naturally, and yes, it does. We know from paleo records that long before humans existed, climate changed. But that doesn't mean that humans can't be responsible for the current climate change, right?
Mm-hmm.
That's a faulty argument just on its face. Another one you might possibly hear is, during the period when, the over 100 million years when dinosaurs were around, that CO2 was much higher. Well, that was, the most recent dinosaurs were 66 million years ago. The Earth was a very different place, right?
Mm-hmm.
Continents were in different places. And just because the sun was weaker, for example, and just because the conditions were with high CO2 were necessarily supporting large reptiles roaming around, that doesn't mean that it would be the suitable climate for human civilization, or the city of Miami.
Yeah, exactly. I totally agree with that. I found that also, that the sometimes counterintuitive effects of climate change, like periods of in locations where there's increased ice, or even like more intense winters, right? Like warmer atmospheres hold more water vapor, right? And so
that's a great example, Dan. I mean, another one that will be trotted out occasionally is like a record of snow extent in the northern hemisphere, for example. Mm-hmm. And it might be trending towards more snow, but like you say, a warmer atmosphere holds more moisture, and because no one's arguing that winter is going to end because of climate change, it's still going to snow, especially at elevation, and a more moist environment in the winter is going to create more snow. There's a lot of, I think that it's easy to take advantage of kind of counterintuitive things, as you put it. Another thing that I think sometimes is taken advantage of is some of these concepts are kind of angled to, and I don't mean this in a pejorative way at all, but to kind of a high school level understanding of chemistry or physics, which are time, students in high school are things are simplified, right? Where in physics, we talk, you do Newtonian physics in high school, and like so ignore friction, right? Like there's all sorts of things that are done to simplify so that the concepts are able to be taken up by students. Now, of course, when if you're Michael Mann and you're a you have a PhD in geophysics, your understanding of things goes far beyond, right? Another really good example that I run into all the time is the idea of gas solubility. And as a chemical oceanographer, you can relate to this. You get folks that say, well, the ocean's warming up, so it must be outgassing CO2 because I know, because of Henry's law, that a warmer solution holds less gas. Well, okay, that's true to a point, but the fact is that the partial pressure of the atmosphere has far more control on gas solubility than the temperature of the ocean, right?
Yeah.
And so trying to kind of push back of kind of half understandings can be challenging at times.
Yeah, and the solubility of carbon dioxide is quite complex too, right? This is
right. It's more difficult than putting a Coca-Cola on a hot plate,
and warming it up. Yeah, it would be nice if it was that simple. It would simplify a lot of our experiments, I think. Right?
I think the students would appreciate it when they prepare for their preliminaries.
Yeah, you also mentioned something that touches some of these questions as well, which is that there are so many myths, right? There are so many different ways of changing things around or plotting things in a deceiving way, right? And I think you hit the nail on the head with the examples you showed, which is that there are lots of different ways of trying to understand the system, but it takes sort of an openness of mind and an ability to sort of walk down like increasing complexity of examples to sort of understand a complex system like the Earth. And so, yeah, and part of that, you showed this well, is that there's so many different ways to sort of pervert that process and make it look like there's debate when there really isn't.
Yeah, another thing you might see is there tends to be kind of an overemphasis on uncertainty, and so and what it essentially boils down to is because climate scientists or oceanographers, depending on what we're talking about, because we don't know everything about a system, we don't know anything. Mm-hmm. And it's like, well, no, I mean, just because we have some uncertainty about the magnitude of CO2 going into or out of the Southern Ocean, it's going in because we have some uncertainty there. That doesn't mean we don't know that the ocean is a carbon sink. Like we know that, right? We're trying to get a better understanding of where and at what rates and things like that. But because we're asking those questions doesn't mean that we don't know that ultimately the ocean is a carbon sink. Is one example.
Yeah, interesting. Yeah, and you mentioned this also, which is the relationship between climate and weather, right? Like we have a great understanding of weather, and we can forecast from compared to when you were born in the late 70s, right? Like the 5-day forecast is significantly more accurate nowadays with all this increase in understanding in the last few years. But there's still limits, right? Like we can't tell you what the weather is going to be like next month, but we can tell you based on historical data that it's probably in July, August going to be in the 90s, right? Right. And so, right. There are some limits to that, but there are also some basic restrictions on it too. So. There's a question here in the chat about CO2 and other types of gases. So the question actually says, there should be little doubt that human emission of CO2 is a large contributor to surface warming in recent decades. But another significant contributor is methane emissions, correct? And there's sort of a question about the specifics of that.
Yeah, methane is really interesting. And kind of, I will be honest that there is some kind of disagreement among kind of methane specialists that I've observed about kind of how significant some of the issues really are. But in a nutshell, yeah, methane is a very potent, much more potent than CO2 in terms of climate forcing, right? But it's also present in the atmosphere at orders of magnitude less concentration, right? So it's much lower. But the one of the real fears is that there's a potentially large methane essentially stock in permafrost areas, especially in the Arctic. And I didn't talk about it specifically in this talk, but the Arctic is warming up about 4 times faster than the rest of the planet, right? And what the fear is that as warming progresses in the Arctic, that these areas of permafrost will melt. And permafrost is essentially layers of soil that are permanently frozen. And so when they melt and they become these environments where methanogenic That's bacteria that through their own metabolism produce methane. What they'll do is they'll chew up all of the carbon that's in the soils and then emit all this methane. And you might hear things like the methane bomb. Now there is some disagreement about how significant a risk that truly is, but nonetheless, we do know that methane, it's a byproduct from our livestock industry, and by our I mean worldwide, not U.S. It's a byproduct of petroleum production. Natural gas pipes are notorious for leaking, and it's essentially been very poorly regulated over the last few years. And so there's potential gains to be made by kind of getting a handle on our own emissions, or especially through leakage of methane. But again, it's present. It's a powerful agent, but it's present at much lower concentrations than CO2 is.
Yeah, and that's a really great description of that. It's a hot topic. You mentioned that really well. That it's a really interesting topic of research, and folks who are interested in methane, there's some really excellent research that's coming out on it, and a lot of it, because it's related to climate. These websites, I'm sure that you've mentioned, Skeptical Science and what's the other one? Carbon Tracker.
Carbon Brief. Yeah, I borrowed some figures from them. They're quite good as well.
Yeah, they'll go into that research and do a great job explaining it too. So, yeah, that's all I have for significant questions in there right now. Were there other things that you wanted to add, or?
No. I appreciate everybody coming to check this out, and again, I encourage essentially it's one of these things where don't necessarily believe everything you read on the internet, right? And no one should be expected, non-scientists shouldn't be expected to have to pore over the peer-reviewed literature on their own, right? And so there are resources that are written to kind of bridge that divide to a certain extent. Mm-hmm. And often websites like Skeptical Science and Carbon Brief, they offer clear descriptions and explanations, but they do tend to steer away from the more kind of hyperbolic coverage of science that you might get in your larger mainstream newspapers or stuff. Because you have to, Washington Post, New York Times do a great job. Don't get me wrong, but sometimes things can get a little overheated, if you will, in the reporting. And I think that resources like some of the websites I've mentioned, I think tend to steer away from some of that and give a more sober kind of explanation of that literature.
Yeah, I totally agree with that. And and you and I, at least, are and a lot of the Skidaway scientists are on social media too. And so if folks in the audience have questions, feel free to pass them along to your neighborhood, if not climate scientists, then climate aware scientists. And we can do our best to try to help parse it too. So a lot of these things that, as members of the public, I think Cliff will agree, we sort through the same type of information and try to sort the wheat from the chaff a lot. So
yeah.
Happy to help you do it.
Yeah, I can be found on Twitter at my handle's at TraceMetalClean. if you're interested in some climate science banter and lacrosse. Among other things.
If you want to know how Lehigh and Florida State are doing also.
That's right. So, buyer beware at that point.
Just at Trace Metal Clean, right?
That's right.
Yeah, that's great. Thanks, everyone. And I think Cliff has this talk for the next evening at Skidaway seminar series. So keep in touch, and we'll see you at the next one.
All right. Thank you.